Hello, let's do 2.1c. So today we will be solving limits algebraically. So sometimes we can just evaluate. For example, if we're looking at the limit as x approaches 2 of 6x minus 3, we can plug in a 2 and do 6 times 2 minus 3. 12 minus 3 is 9. Sometimes it's that simple. Sometimes we have the limit of a constant. Keep in mind that constant is technically a function. So if we're looking at the limit as x approaches 7 of 3, let's think about what this really is. Let's draw a coordinate plane over here. Technically that 3 is actually the line of the function y equals 3. Okay, and so then we're looking at as x goes to 7, let's say 7 is right here, what's our y value? Well, it's 3, because it's always 3. So that's always true. The limit of a constant is just a constant. So let's try a couple. Let's try the limit as x approaches negative 1 of x plus 2 over x squared minus 4. And let's try the limit as x approaches 4 of pi. Pause the video for a moment and try these. Okay, welcome back. I'm assuming you paused the video for at least, a couple seconds. So for the top one, if you plug in negative 1, you end up with negative 1 plus 2, which is 1, over negative 1 squared, which is 1 minus 4, which is negative 3, or negative 1/3. And the limit as x approaches 4 of pi is just pi. Because again, this is just technically like the line y equals pi. And as x approaches 3, or as x approaches anything, y is going to be pi. Sometimes you have to manipulate algebraically in order to find the limit. So you have to make it look different. So for our third example, the limit as x approaches 0 of 1 over x squared. Well, in this case, 1 over x squared is 1 over 0, so this does not exist. Okay, the limit does not exist because you really can't divide by 0. That's still true. So anytime you have the limit of a number over 0, there's no limit, or it does not exist, or DNE. Sorry, turning my page. Fourth example. The limit as x approaches 2 of x squared minus 5x plus 6 divided by x minus 2. If we evaluate for 2, because again you should always do that first, we get 0 over 0. So this is inconclusive because are we taking 0 divided by a number, or are we taking a number divided by 0? I don't know. So we know this is a whole was odd. Or a removable discontinuity, and we'll talk about that kind of stuff more in future. So whole or removable discontinuity. So we need to write this differently to find our limit. So we can factor. That happens a lot. So we can factor x squared minus 5x plus 6 into x minus 2 times x minus 3. In the denominator, we still have our x minus 2, and now we can cancel out that whole. And so this is actually the limit as x approaches 2 of x minus 3. And now we can evaluate, and 2 minus 3 is negative 1. Note, keep in mind, whatever you want to call it. So we figured out the limit as x approaches 2 of x squared minus 5x plus 6 over x minus 2 is negative 1. But f of 2 doesn't equal negative 1. That's why it must be a whole or a removable discontinuity, because that's where it looks like it should be at negative 1, but it's not actually there. Let's try some more. Let's do the limit as x approaches 4 of 3x over x squared minus 16. The limit as x approaches negative 3 of x squared plus 7x plus 12 over 4x. And the limit as x approaches 2, x squared plus x minus 6 over x squared plus 6x plus 9. Something I want to make note of before you pause your video is you have to keep writing the limit notation until you evaluate, which just means until you actually plug in a value, you keep writing limit. Once you plug it in, you don't have to anymore. Okay, pause the video, try these problems. Okay, I hope you tried them. So for the first one, start out by just evaluating. We end up with the limit as x approaches 4 of, well, 3 times 4 is 12 over 4 squared minus 16 is 0. Again, do we have to write lim here? Not necessarily, because we evaluated it, but you always can. And if you can't divide by 0, so the limit does not exist, DNE. For the next one, we evaluate, because again, that's what you should always try first, no matter what, because that happens a good amount of the time. Negative 3 squared is 9, plus 7 times negative 3, so 9 minus 21 is negative 12, plus 12 is 0, over 4 times negative 3, which is negative 12. 0 divided by a number is just 0, so our value of the limit is 0. That we can evaluate. The limit exists, it's just 0. And for this last one, okay, so if you straight up plug it in, you get 0 over 0, which tells us a whole lot of nothing. So let's try again. Let's factor. So the limit as x approaches 2, if we factor this, x plus 3 times x minus 2 over x plus 3, x plus 3, cancel out our whole or removable discontinuity. So this is really the limit as x approaches 2, because again, we haven't plugged in yet, of x minus 2 over x plus 3. 2 minus 2 is 0. So limit as x approaches 2, 0 over 5. Our limit is 0. Okay, Just to emphasize, I'm going to put a box around this because it's important and I don't want it to get lost in the solution. Okay. Change the colors again just for fun or something. Oops. There's one limit we can't reduce. The limit as x approaches 0 of sine x over x. Because if you plug in 0, sine of 0 is 0, and 0 is 0. So what does this mean? There's nothing to simplify. A sine x and an x, you really can't do much. However, if you look at the graph, it looks something like this. And you're welcome to graph it yourself, and it'll look a lot more exact than my pretty picture. But if you have a coordinate plane,